Hello, let's do this question. Longest increasing subsequence. You're given an array of numbers and you want to return the longest increasing subsequence. So that numbers not necessarily contiguous with each other in the original array, but are increasing. So if you take this one for example, the longest increasing subsequence, well, if you only consider the first element, the longest increasing subsequence will be just 10. If you consider these two, longest increasing subsequence could be either this one or this one. Let's just take a 9, because if we take 9 as the longest increasing subsequence for this problem here, this sub-problem, then it gives us a better chance of having a longer subsequence if we consider larger sub-problems. So let's just take 9. So let's consider the first 3 elements, and the longest increasing subsequence would be 1. So you can have 10, 9, or 2. Let's just take 2 because it's the lowest, and it probably gives us the best answer so far. Then considering the subproblem for the first 4 would be 2, 5. So I guess it would be the longest increasing subsequence of this part, and then you add this on. But it's not that quite simple, as we'll see. So let's consider the longest subsequence of this part here, and that would be either 2, 5 or 2, 3. So we could either take 2, 5 or 2, 3, but in this case it's probably best if we take 2, 3, because that gives us a better chance of having a longer subsequence if we take larger subproblems. And then let's consider this subproblem here. So this is we know that for the previous subproblem this was the longest increasing subsequence. Then we're taking one more, 7, and 7 isn't smaller than any of these, so we could just add it to our longest increasing subsequence. Then we consider another element in our subproblem. It's also fine, and we consider the next one as well. For next one, it doesn't increase it. But because our formula is kind of greedy a little bit, so we can remove the 101 and get an 18 instead, and this would be our answer. So our answer would be 4, the length of the longest subsequence. Yeah, so that's kind of the idea. If you kind of brute force this though, this is the optimal solution, which kind of came naturally by thinking of it in terms of subproblems. But if you had like a brute force approach, you could have done the n squared sort of by considering for a particular number what is the maximum subsequence length given all the previous numbers before it that are less than the current element. So there are no numbers less than 2, so the longest increasing subsequence of 2 would be 1. Oh, there's one number less than 2, so we're forced to take its answer, which is 1, so then it will be 2 here, and then this one, we could consider all numbers less than 3, it's still 2, so that's also going to be 2. For 7, we consider all numbers less than 7, so 2, 5, 3. Out of all of these, which has the highest subsequence length, it would be 3 or 5. Yeah, so that's kind of n squared, which also works, but this way is more efficient. So yeah, we could try both, but might as well jump straight to this one. Okay, but let's actually see what happens if I continue another subsequence that is quite low, so maybe 4, 5, 6, 7, 8. So right now the longest subsequence is this at this position, and then we add 4. When we're at 4, we actually want to replace 7 to be equal to 4. This doesn't actually change the length of the longest subsequence so far, but we can use this to find out the longest subsequence so far. For larger subproblems, even though this isn't really a valid subsequence. So we get to 5, and what do we do at 5? We see for 5, what do we want to replace? Probably 18. So essentially we want to replace the number greater than or equal to 5 within this array. And since the array is sorted, you could probably use some kind of binary search to find the first number greater than or equal to the current. And so it will be 18 here, so I can replace that with 18. So now it's valid, so it's 2, 3, 4, 5. But even if it's invalid or valid, the number of elements in that subsequence so far is still correct. It's still the maximum subsequence length that you could actually get. 6 as well, and 7 and 8, just add to it. Alright, so let's try and implement that. So what we can do is have an array nums, let's call it dp, and there's nums.size elements in there. And also want to keep track of the length, so where I'm up to in that dp array. So we go through all the numbers and we search for basically the upper bound. So we could do a binary search to find the number greater than or equal to the current. Not the upper bound, the lower bound. So lower bound would mean greater than or equal to, upper bound would be means greater than. So in this case we want the lower bound. So it is equal to the lower bound of dp. So I would like to do dp.begin and dp.end, in which case it would be easier if I actually use a vector of ints for dp and make it have this size here. And what am I searching for? I'm searching for n. Now this value may not exist, so if it doesn't exist, if iterate is equal to dp.end, that means I want to do the dp at the current element. So what does it mean that I can't find an element? It means that the number so far is the greatest. So I could just add it to this subsequence. So I can say the length is equal to n. And I want to increment length afterwards. Otherwise, I just want to replace the value to be equal to n. Because I've searched for the first element greater than or equal to n, that means if I replace the value, either not doing anything at all or decreasing that value at the found position. This is basically what we're basically implementing what we're talking about here. So then let's at the end just return the length. Oh, seems to be an issue because I'm searching for dp .end, but end is actually the end of this. I actually want to have dp.begin plus the length so far. So if this is equal to begin plus n plus the length, means I haven't found it. Yeah, let's give it a go. Cool. So the time complexity of this would be n log n. So it takes log n to find the lower bound, and we're doing that n times, so n log n.